Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, today we're pleased to have David Aldous speaking, who's going to be with us for a couple more weeks. So if anybody would like to talk to him afterwards about random spatial networks, I'm sure he'd be happy to talk.
Okay, thanks. So this is the first talk on what I've been thinking about for a while. So disadvantage of being a first talk is that there are some fancy graphics that aren't there that you'll have to imagine. So okay, what are we doing here? The actual content of the talk is some math theory about sort of inventing and studying a sort of class of slightly abstract, but hopefully not too much general nonsense, random processes, a kind of axiomatic setup, etc., etc., etc. Before getting to that, there's some sort of a background, and so the first part, I want to make a kind of obvious conceptual point. There's a difference between data and sort of a specific model for data and classes of processes, kind of obvious, but maybe easy to forget. So the next two slides are going to deal with that, as well as life, universe, the universe and everything. Pretty impressive in 2 slides. The other bit of the general background is we talk about road networks. So I kind of want to talk about view of road networks from paper maps and the view of road networks from online services. Again, it's a weird thing to talk about, but it actually influences how we're setting up our math model. So here are sort of 4 quite chosen to be very different things that, real things that we can choose to look at as data. Different aspects of the world. So one aspect of the world is the physical world independent of human beings. So the top left is a bit of coastline of Italy. So another part of the world is the human social world, the relations between different people. So bottom right is a graphical representation of a social network. So third bit of the world, look around you, what do you see? Well, you see people's faces, hands. Everything else you see is a human artifact. Kind of forget that. We live in a world of human artifacts. So there's the engineered world. So top right, the national highway system of the United States, sort of part of the engineered world. Of course, the sort of fourth world we live in is a world of ideas, emotions, motivations, illustrated by a quote from Hamlet. Okay, so there you are, life, the universe, and everything, or for 4 aspects of it. So of course, none of these things are mathematics at all, so they're sort of actual things somehow. Nothing, a priori, nothing to do with mathematics, but we're all sort of math nerds here, and so one can sort of approach anything with a mathematical eye and sort of try and find some mathematical aspects of it, and we kind of all know that there are, the particular things here I chose rather carefully, that there are mathematical aspects of them. So let me sort of come back to them. They sort of all fit 4 of these 5 classes of things, but let me sort of jump slightly here. That, again, there's a difference between data and a particular process, thinking of as a model for data, and a class of processes. And so the sort of familiar classes of processes perhaps are the top 2, sort of stationary processes and finite state Markov chains, so sort of very kind of explicitly defined math objects. But there's sort of classes of processes. So if you now think of a particular process, so a particular stationary process, and to be pedantic, sort of a finite valued stationary ergodic process. Second layer, I'm thinking of sort of irreducible finite state Markov chains. If I take a particular process in that class, then it has sort of several interesting numbers, and I'm focusing on one of them. For stationary process, an interesting number is entropy. For finite state Markov chain, an interesting number is mixing time. One can kind of go through a list of different things here, where you have classes of process. So the trouble is, if I start off talking about classes of processes, it kind of sounds like general abstract nonsense, and maybe it is. So how do I stop it being general abstract nonsense and try it something more concrete? And so the first 2 things illustrate that for every process in this class, there's this particular number, and the number is both interesting as theory, because the entropy of a process sort of says something about how we can compress it, and then the mixing time of Markov chain says something about other properties of the Markov chain. And also, as well as these theoretical things, you can actually try and estimate them from data. If you're having data for something, you can kind of to try and estimate what these theoretical numbers are. So you could go down the list. A random fractal isn't such a precise class of objects, but we kind of recognize it when we see it, and somewhat tautologically, the interesting number associated with a fractal is its fractal dimension. To give us sort of an interesting thing I don't know how to talk about, social network models, we kind of recognize what a particular model is sort of something you might use to model a social network. Again, there's no actual sort of general definition of a class of social network models analogous to the other classes. It would be interesting to have one, and it would be interesting to sort of fit into this schema whereby you could say, well, there's a class of models. For every particular model in this class, there's an interesting number. And of course, people sort of do this badly by thinking of these as generic complex networks, and thinking of degree distributions having power law tails and using the power law exponent as a statistic. But that's kind of dopey. Everybody does it, but still dopey. So anyway, so this is sort of something where sort of I don't know a good way of doing it, and if you found a good way of doing it, you'd become famous, and Jennifer Chase would offer you a job. So this is a kind of interesting open area. What I'm going to talk about is something sort of is in this same genre. So the point of all this spiel is to try and get into that what I'm actually talking about is sort of a class of processes rather than a precise model within that class. I'm going to talk about a class of processes, and it has this same feature that for every process in this class, there's a sort of an interesting number, an interesting statistic associated with it. Don't have a good name for this, so again, small prize or fame for anyone who sort of suggests a name for something that I'm unimaginatively calling P of 1. So anyway, okay, that's the conceptual stuff. So let me go on to actual road networks, etc. What kind of math object should we model a road network as? So at one level, this is simple. So this is the simple level. At the bottom, and a few of these slides, people who've seen previous talks of mine will have seen before, at the bottom, sort of Xerox out of the Rand McNally Road Atlas is kind of a schematic for the intercity road network of the northern parts of the United States, kind of cities and lines and distances between cities marked on them. So that's sort of real data. And again, the type of mathematical, on the top is sort of a mathematical thing. There's sort of a set of points in the plane, which are actually chosen at random, and then edges between points chosen according to a particular rule. And it's clear that the real world thing, a mathematical representation, as Rand McNally well knew, a mathematical representation of the real data here is this type of math object. There isn't any mystery as to sort of the natural way of thinking about this. Of course, having a sort of accurate specific model is harder, but the sort of type of object isn't mysterious. So this is sort of one thing where it's clear conceptually what I want to do. At another extreme, the sort of road network within a city of Manhattan or Redmond, we kind of know what maps the road networks of a city look like, and it's not particularly mysterious to think that we model them as grids or variants of grids, etc. On the other hand, I want to think big, and I want to be, forgetting what, let me take that back a second. I want to imagine what a sort of online map has, which actually understands the entire road network of the United States, and I want to think about what is the mathematical model for the entire road network of the United States. Now let me pull out and do a slightly better graphic here. I'm going to do my, where is everything here? Escape. How does this work? Somewhere up on here. Ooh, this may end up as a disaster. Let's go here. No, that's not working here. Oh, it is working here. Do I actually have the... I should never have tried this. Just a moment. Went to the wrong thing here. Why am I not going to... I got the wrong one. Oh, okay. I'd done the dopey thing of having an actual slide of what I wanted to look at and the actual web page. Okay, so I'm going to stick with this. So this is this is my slide version of something that's the actual web page. Yes.
You say road network, how much does it depend on the politics of the country? Like the US being a federation and France being very heavily centralized?
That's a good question, and I don't have it, but even if you look at different states, so if you look at, say, Iowa and Indiana, which flat Midwestern states, you might not expect the road networks to look different, and they actually look very different because sort of Indianapolis is sort of like the Paris of Indiana, and everything, all roads lead to Indianapolis, and sort of Iowa, they were these Cartesians, and they kind of have this thing. So yeah, so for historical reasons, but that's kind of precisely my point, that if you want a model, if you want to write down one model that fits everything, then you have this sort of trouble, but I'm not trying to fit to one model, just like English language and French language is different. So instead of a particular model for this, I want a class of models analogous to stationary processes as models for sort of natural language. Anyway, so this is, again, doing something that a priori sounds crazy. This is the entire road network represented as 25 million or so line segments and nothing else. That's what's sort of impressive about this. This shows road segments and nothing else. It doesn't show borders, it doesn't show coastline, it doesn't show cities, mountains, rivers, anything else, just roads. And so now, of course, you can infer the borders and the roads within the United States, so you can infer the boundaries from there. What should cities look like? Well, cities, there are lots of roads in, so the sort of dark blobs over on the right are cities, and you can really test your knowledge of American geography by trying to identify all the cities that are sort of lying around here. Let me try my pointer here. So yeah, exactly which city is all of these things here. It's not so easy to figure out. So that it's just slightly clearer. And I can try again and find it. Well, this is one. I have two web pages here somewhere. It's my trouble. So I need to go find the other. Somehow it's gone. I had two tabs up.
Why don't you codify that?
And reopen closed tabs. Okay, what am I doing here? It's not doing things.
I think you had two browsers. It's not in that browser.
I thought I was supposed to have two tabs, and I'm kind of losing things, which I probably don't want to lose here.
So if you mouse over the
I'm sorry, I'm not sure what you're... Yeah, okay, yeah, anyway, no, so you're right. Ben's right on all streets. So it's slightly clearer on the actual page, but not hugely clearer. So if I'm going off topic, so the other cities are easy. Over here, we automatically think you're seeing mountains and topography, and you're not, of course. So you're seeing something different, completely different over here from what you think you're seeing, because we're kind of actually seeing cities in the Central Valley rather than the Sierra Nevadas. Anyway, I digress. The point is that this is sort of a bit like jokes about mathematicians. This is literally true, but it's, of course, completely useless as actual roadmap for the normal sorts of things we use roadmaps for. So that was just sort of a bit of a fun digression. I want to make an obvious conceptual point that old-fashioned we grew up with old-fashioned paper maps, and now we have our online road maps, and they differ in two ways. So for a paper map, you have to start off deciding there's a level of detail you're showing, and that's what you've got. And of course, the point of online maps is that you can zoom in and out. Here's a large-scale map that only shows major roads, and I could zoom in. I won't try and do the demo, practice these demos. You can zoom in, and you see a smaller area, and you see more and more detail. There's a spectrum of major to minor roads we'll talk about later. But kind of at the obvious common sense level, we see the minor roads as we zoom in. So you don't have this sort of pre-specified level of detail. And secondly, you can ask your online service for an actual route between two addresses. And again, we're not talking cities, we're talking individual street addresses, so 100 million, 150 million, that order of magnitude of street addresses, and you could actually get a route between any two of those. So there's sort of roads and there's routes, which obviously are related, but I think are slightly different. So the idea, I'm sort of working towards the setup for a model. The idea is I want to kind of think of routes instead of roads as the primary object, and I want to sort of abstract Bing Maps, Google Maps as an oracle, instead of 100 or 150 million points in the plane, I'm being a mathematician and want to think about the continuous plane. So I want to imagine big maps as kind of an oracle. For any 2 points in the plane, I'm going to get a route between them, and that's kind of the way I understand this process. So again, it's analogous to sort of ergodic theory view of English text, that Hamlet is one realization from a stationary source. I want to think that what's inside my abstracted Bing maps, that is the actual US road network, is sort of one realization of some rather complicated abstract process, but we sort of get at this realization by sort of asking it for routes. So that's the sort of way I'm going to do a math model. Again, we're going to say a bunch of assumptions, but the sort of interesting one is the scale-invariance assumption, so the fact what makes this sort of a theory. So I'll say it intuitively. So you have to imagine low tech. I put 7 points on a bit of transparent paper, the old transparency, and now I get a paper map, and I sort of take my transparency and sort of randomly position that somewhere on the paper map, and then I look, those my points on corresponding to real positions in the United States, find the sort of nearest address, and sort of ask for the routes in the actual road network between each pair of points here. And we're getting something like this: 7 points, 7 choose 2 pairs of points. I put all those routes together. So this is a kind of sub-network of the real network, but kind of looked at on the random points somewhere. So there's some statistical distribution for what I see in a sub-network like this. And the idea of scale-invariance is that I haven't told you the scale of the map I'm looking at. The width here could be 5 miles or 25 miles or 100 miles. And scale-invariance is saying that the statistical properties of what we see here don't depend on the scale. That you couldn't tell from this, it wouldn't be sort of more likely that this came from something 5 miles across or 100 miles across or not. So of course, to what extent this is empirically realistic is a bit dubious. It's not actually as crazy as it sounds. I always like the quote about Wagner's music, famous line. Wagner's music, it's not as bad as it sounds. So this is kind of the same sort of thing. It sounds completely crazy, and it's not completely crazy. So little comments about scale-invariance. So this is the sort of screenplay for a movie I haven't written. Kind of screenplay for Avatar, maybe not exciting as a thing. So Wikipedia, I'm going to try again with my little thing here. Somehow I'm not doing this. Okay, I'm not. I just lost it. I am not. I have a bad instinct for these things. Okay, we're going to abandon these things anyway. You use all your imagination. So you have to imagine 4 things instead of 3 things here. So what Wikipedia Wiener process has this dynamic picture which zooms in to the a Brownian motion sample path, and so you're seeing the scaling invariance as you actually zoom in here. And yes, we can see that at the end. So there's a lot of dynamic demo of scale invariance as you sort of zoom in on 0. If you then sort of took something you might actually model by Brownian motion, like the S&P 500 intraday today, you could attempt to do the same thing with data. Kind of might work for a while, but of course eventually there's some bottom line where the Brownian motion model eventually breaks down at some fine scale. But we sort of don't care too much about that because models don't work the same way. So anyway, we can sort of imagine on our real road maps are like the stock market data. You can actually zoom in some number of levels, maybe 15 levels between the world as a whole and the sort of finest resolution of individual houses. There's some finite number of levels, because at the end you can't zoom in, there aren't arbitrarily small roads, but that's kind of like zooming in on a stock market during one day. And again, we could go back, just like the sort of mathematical Brownian motion on Wikipedia, we could go back to a realization of the models I'm talking about, and then of course you could zoom in forever. They're mathematical objects, and you can zoom in already or forever. So future movie there. The final point to emphasize is that scaling often comes in the context of scaling exponents. We're doing sort of naive Euclidean scaling without any scaling exponents, which is just that if I shrink everything by 2, then sort of everything shrinks by the same factor, and we'll come back to that in a moment. Before I get to axiomatics, I'll end the introductory part by speculations on the same theme of maps and scalings by a famous mathematician from 120 years ago, who was the most well-known person who was also a mathematician 120 years ago. So I'll let you read this in peace. Anyway, so I'm not sure what Lewis Carroll would think of our modern technology, but that's his thought on paper maps. Okay, so going to math, there's an axiomatic setup. The details are technical in a boring way, which I'm not going to tell you, but we're thinking of we're given a process. So what are we given as mathematical objects? Well, kind of going back to your old-fashioned way of looking at stochastic processes or things like Brownian motion, you're given finite-dimensional distributions, FDDs, so in this context, yeah.
In the US, with its quarter section, do you really expect to be rotation invariant? So many old field boundaries go north, south, and east.
Yeah, you're right. The things aren't really rotation invariant. In some sense, rotation invariance is just laziness, like assuming stationary processes are ergodic, because you could just add a random rotation and force it, and it doesn't change anything. So it's just a sort of a tidying, bookkeeping rather than anything that's actually important. Yeah. So it's just it makes formulas simpler. Yeah. So it's not actually important. I mean, yeah. Okay, so we imagined, again, it's this idea that we can sort of query the oracle, and what this basically comes down to is that I can put in a finite set of points and get routes between each pair of them. And again, because I'm thinking of, I'm seeing one realization of a random process, but I'm sort of modeling the random process. And so the distributions of these structures are sort of Kolmogorov consistent in a natural way as things vary. And the assumptions, again, translation and rotation invariant. Of course, things aren't literally that because of kind of population density, etc. It's just sort of simplifying things. And, scale invariant is the sort of real sort of meat of the assumptions. Because invariant under kind of naive Euclidean scaling means that, if I take two typical points at distance r apart, there's some random route length, the distance by road between them is some dr bigger than r, and this is just sort of scaling linearly. And distribution here, I could just scale points 1 apart to points r apart, so the distance, the route length between 2 points, distance r apart, just scales as r times the distance for 1.
We're not non-intersecting pairs?
On non-intersecting pairs. Okay, good. I'm going to come to that later. Yeah, thank you. Yes.
What does FDD and Kolmogorov consistence mean?
FDD is finite dimensional distributions. So the way you think about the sort of Kolmogorov consistency theorem. Kolmogorov consistency is kind of the idea that the simplest version is that in order to define the distribution of an infinite sequence of random variables, it's enough to define the distribution of any finite subset, kind of with the obvious consistency thing. Yeah, so it's sort of back. The measure theory operating system for probability. Yeah. We want to assume, because we're modeling roads, not something else, we want to assume that these distances are finite, which isn't as, which kind of relates to another bit of work, David Wilson et al. 10 years ago, and of course much subsequent work, that if you start off with models, various models of random spanning trees in the plane, you do random spanning trees of the lattice, and then refine the lattice and take limits, then you can get random trees in the plane, which of course, trees are a special sort of road network if you want to think about them. But these trees kind of have fractally paths, so the actual lengths, the actual distances on a tree-like road network in the plane are going to be infinite, and we want to sort of exclude that. if there were a fractal road, I wouldn't want to drive along it. So it's finite. The second thing, again, going to what Asaf was saying, intuitively we think that what Bing Maps is telling us, so in the real world network there are sort of many paths from one place to another. It's picking out one of the many paths as the route. It's programmed to do that by minimizing something, not necessarily route length, because maybe it wants to put you on fast routes, so it's minimizing something we can think of as the actual driving time. To put that into an axiomatic setting, kind of, you need another layer of assumptions, so we want to assume something weaker. So the idea is that for 2 points here, there's a route. For 2 points here, there's a route. And what sort of isn't allowed is that sort of this route does that. And we sort of don't allow that for the obvious reason that somehow, both routes are going from between those 2 points, so they should be using the same route between those 2 points. So that's a sort of compatibility property, and again, it's sort of implicitly not allowing paths to self-intersect. So these are rather weak compatibility conditions we throw in. Again, so we're thinking of a process, we're thinking of routes between everywhere and everywhere else, which is rather hard to get our minds across. And the way to start thinking about this is to, again, instead of trying to think of routes from everywhere to everywhere else, we sort of sample points in the plane according to a Poisson-point process, and just look at routes between pairs of points within the process. And so we're imagining this, again, going back to my pictures here, I'm imagining something like this, but now sort of spread over, the points are now spread over the infinite plane, and again, we're looking at routes between each pair of them, but we're imagining that we want to say that within a window, we don't fill the whole window with roads. We're still seeing a kind of a discrete pattern of roads within a given window, and this discrete pattern of roads is saying that when I look at all the routes between points of a Poisson process, I'm still having some sort of finite mean length per unit area. It's not going up to infinity. Again, in a sense, there's a network where for every pair of points in a plane, I draw a straight line between them, but that's kind of silly. I don't want that. So the final assumption, again, these are sort of technical things. The main assumption so far is the scale-invariance. There's one more assumption that turns out to be the interesting thing. And again, I'll say it informally and then re-say it in a nice way. So I want to go back to my sort of Poisson point process of rate lambda in the plane, but I'm just going to show the points of the process in these two regions, and then I'm just going to show the routes between some point on the left square and some point in the right square. So I've got 3 points and 2 points, I've got 6 routes, and I sort of put them all together. And now the idea is I sort of go on increasing lambda, so I'm sort of sampling more and more points in the left square and the right square and looking at the routes between them. And I got lazy with drawing my picture at this point. But what I'm saying is that what's going to happen as I sort of look at more and more street addresses here, more and more street addresses here, and keep asking for the routes, well, I'm going to see sort of more and more bits of roads in here, more and more bits of roads in here, occasional sort of road segments from a point near here joining that. But basically, they're only, in the real world situation, there's only a sort of fixed number of routes, say the 3 I've got here, there are only a sort of fixed number of places, there's sort of a major road which connects somewhere in here to somewhere in there. And so that's something that kind of intuitively clearly happens. Really, in the real world, and we're going to put this into our model, and that as lambda goes to infinity, however many points we sample, we're just ending up with a sort of finite mean number of crossings of an intervening line.
So the two squares are separated?
Yeah, they're separated, of course, yeah. And again, that's the kind of the intuitive way of saying it. There's a nicer way of saying it. Again, let me go back to this all sort of relates to both technical and conceptual points of, Kolmogorov consistency works fine for countable index sets. When we go to continuous time processes or uncountable index sets, we kind of have to start worrying about measure theoretic niceties and sets of measure 0 and uncountable unions and things like that. And the kind of standard way of doing this since Scholarhard in the 50s started thinking about convergence is to say, well, in order to talk about the process as a whole, you want to think of it, the process as, not as a collection of random variables, but as one object taking values in a function space, continuous functions, Cadillac functions, etc. So that's the kind of standard way we now think about continuous time processes as a whole, so rather than just their FDDs. It's kind of, it's hard to know how to do this directly in our world because, firstly, the xt is something simple like a number typically, whereas our individual r's are these slightly complicated graphical arguments that are paths, so they're in some space of paths that I've spared you from giving a definition of. And then if you want to think of sample path properties, you're now saying how does the path, what continuity properties does the path from Z1 to Z2 have as a function of Z1 and Z2, and again, sort of building this up at the beginning is a bit of a pain to put into an axiomatic setting. So that's sort of one technical issue in order to talk about this kind of continuous parameter process. As a whole, we need some regularity conditions to sort of knit together the finite dimensional distributions. If we think about real-world networks,
one method initiated by Oded and studied with Smirnov, which is just to record for which quadrangles you have a left to right crossing, which you have.
Okay, yeah, I think there are lots of technical ways of doing it. I'm going to kind of claim a conceptually simple way of doing it. Which you can argue about later. Yes. So the kind of conceptual point of the real world point is that we have an intuitive notion of major roads, minor roads, freeways, the dirt tracks, etc. To actually quantify that in the real world, again, there are several ways of doing it. How big is 148th Avenue out there? You can kind of quantify that as the number of lanes. You can work within the sort of numbering system of interstates, US roads, state roads, county roads. You could do it more continuously by a measure of traffic volume. These are all sort of roughly correlated with each other. And of course, maps show this. This is actually an important point of sort of real maps. We're doing a model where the model just gives us routes as sort of mathematical paths in the plane, without sort of saying that here I'm on a freeway and here I'm not on a freeway. That's kind of, we're putting minimal things into our model. But the kind of interesting thing, first interesting consequence, is that we can sort of derive a notion of size. Again, size, and I should think of a better word, point on this minor road to major road spectrum. We can sort of derive a notion which isn't quite as natural as the real world notions, but is still sensible. Again, to be technical, we have to start, we're given FDDs to start off with, so we can't sort of talk about kind of every point simultaneously, but we can talk about the network on our Poisson processor points, because that just depends on sort of FDDs. So what we're doing is, conceptually what I'm doing is taking a sort of a small piece of asphalt, a small part of the road network, and then I'm sort of taking a distance, fixing a distance r, and I'm now saying, are there 2 points, both of which are at least a distance r from this particular bit of asphalt, such that the route from one to the other goes past where I'm standing now. So the point is, if I'm just out on 36th Street here, then kind of no one driving from somewhere 10 miles away to somewhere else 10 miles away goes along 36th Street outside the building, whereas maybe there's some maximum distance. I'm not sure. There's probably points 5 miles away in north and south, so that someone would be driving between those 2 points 5 miles away, would be going down 148th past the building. So we get for each r, there's a sort of a subnetwork of the network, a subnetwork of the Poisson sample network, consisting of points on roads that are on a route where sort of both endpoints are more than r from where you are. Now the point is that that sort of rigorously makes sense in terms of FDDs. And now we can let lambda go to infinity. Everything's monotone, so there's a sort of lambda equals infinity limit, which we can interpret as the parts of this sort of entire network, the network on the continuum, with the same intuitive interpretation, these are points on a road that are on the route between some pair of points in the continuum that are a distance more than r from where we're standing. Again, everything's stationary, so this sort of subnetwork has some mean length per unit area depending on r. Scale-invariance, which does all our work for us, shows that this scales in a particular way, and because their final assumption kind of implies a previous assumption is that these rates are actually finite. Again, sort of a priori you might have, they might be infinite, but our final assumption is that these are finite. So these assumptions, which the important ones are sort of scale invariance and this finite one, again, define the class of processes. We haven't sort of defined a particular model here, but it's a class of processes, like stationary processes is a class of processes, so jargon, scale-invariant, random spatial networks. And I'm claiming that the interesting number, as my sort of philosophical thing at the beginning, any particular process in this class has an interesting number, which in this context is this p of 1. Let me kind of say why this is interesting. Maybe I'll say it first and come back to the previous one. Firstly, this is, I'm doing bad ordering, the condition that P1 is finite is the sort of mathematically tidy version of what we were saying back here. That's basically the same condition as saying that however many points I sample on the left and the right, that there's only a finite number of crossing points on an intermediate line.
I have an assumption here that these two squares are far apart.
It doesn't matter because everything's scale invariant. So it doesn't matter. There's just some some distance. This is 1, this is 1, this is 1.5 or 2, and however their scale doesn't matter. Bigger than 0. Yeah, bigger than 0.
Adjacent.
Well, no, you're going to have infinite number of things across the boundary if they're adjacent. Yeah.
Separated by a few inches, maybe there'll still be infinite number.
No.
Well, no, but it's ratio. I mean, it is kind of constant. I mean, the ratio, the ratio of sort of this length and the separation has to be not going to 0 or infinity. But yeah, but it's just yeah. Okay. Right. So this final assumption kind of corresponds to that picture, the conceptual level, but it also kind of works as the sort of technical regularity assumption, analogous to sort of regularity conditions on paths for regular continuous time processes. That sort of the FDDs, consistent FDDs plus this assumption kind of gives us this limit structure. And this limit structure is somehow, we did have Poisson sampling as an intermediary, but somehow the effect of the Poisson sampling goes away at this point. And we've sort of gotten a picture, sort of which, as r comes down from infinity, for large r, this is showing what we imagine as just the interstate freeways, and as r comes down, we're showing sort of more and more minor roads that are sort of slowly sort of filling in the entire plane. And again, this is sort of a math object whose sort of existence follows from the previous setup. And finally, of course, the actual number, P1, is a number. For the real road network, it's probably 2.5 or something like that. Again, it's a pure number. Everything inside is scale invariant, so it actually can't depend on whether you're dealing with miles or kilometers, etc. It's a sort of characteristic of a particular model. And kind of saying it backwards, this way of looking at things gives any road segment gets sort of assigned a real number r, the smallest r, such that you are in the route, or rather the largest r, for which you are in the route between 2 points at distance more than r apart. And that's the sort of where you are on the spectrum from minor road to major road. Going back to, again, the last bit about the axiomatic setup is, so there are technical reasons for doing it this way. So we chose one of sort of 3 possible ways of starting out here, which is imagining how Oracle gave us routes. Another sort of common sense way of doing it is, well, let's start off by putting down the major roads and then fill in minor roads, etc. a more mathematical way of saying this is saying, well, let's just make up a random metric on the plane and define routes as geodesics in the random metric. And so 2 and 3 are perfectly sensible ways of trying to invent particular models in this class. When you try and sort of do rigorous constructions, the actual technical problem, as far as I can see, is proving uniqueness of routes. And somehow 2 and 3 don't help you with the uniqueness of routes. So if you start there, you kind of have to assume uniqueness of routes too in general. And if you're going to do that, then kind of only assuming uniqueness of routes to begin with seems, again, conceptually tidier. So that's kind of why I'm doing it that way. So let me go back to the beginning and show this slide again. Where are we? The bottom stuff is what we did first. There's an axiomatic setup. Again, a class of processes. So what are the properties of any given process in this class? And I sort of started saying some with this kind of emergence of the road structure. There are some more mathematical ones I'll say very briefly here, and they partly relate to issues in percolation type theory. So there's a notion of a geodesic, which is slightly fussy in detail in this context, with sort of a semi-infinite or a doubly infinite. Geodesic is sort of an infinite line such that arbitrarily long finite sections of it are in routes. So it turns out to be elementary that there aren't any doubly infinite geodesics, and sort of the analog of this in various in more standard first passage percolation problems is sort of hard open problems, but here kind of scaling invariance and symmetry gives us a lot for free. When it comes to semi-infinite geodesics, if I take one picture, 1 point without loss of generality, the origin, there's a route from here to anywhere, so I can kind of let the endpoint go to infinity and take limits. So there have to be, so there has to be at least one semi-infinite geodesic out to infinity. A priori, there might be more than one, and of course, a moment's thought thinks that the only possibility is that they'd have to be some tree-like structure. That's just sort of the nature of geodesics. The only thing that they could be is a tree-like structure. On the other hand, if I then say, well, how many of these are sort of crossing a circle of some radius? On the one hand, because they're tree-like, the number of crossings can only increase as you branch. On the other hand, scale-invariance tells you magically that it has to be constant. So the number of crossings has to be constant. Of course, could it be infinite? Well, it could be infinite, except P1 less than infinity stops it being infinite. So there's a sort of finite number. Could it be 7? Well, maybe it could be 7. There may be some weird examples where there are every point, or almost every point, has exactly 7 infinite geodesics. It's kind of like having sort of 7 infinite components in a percolation problem. It sounds very implausible somehow. So, say it again. I'm not sure how it rules out 7, actually. It may do, but I don't quite see it. Okay. Right, no, it isn't shorted. There's a route from 0 to anywhere, and right, there's a route from 0 to anywhere, and then the idea is that so the route from 0 to here may go along here, and then the route from 0 to here might go around there. So a geodesic, you kind of have this odd property that sort of things are only precisely defined almost everywhere, and roads have measure 0. So actually, you right. There are a lot of technicalities I'm hiding here. Sorry, you well?
I just want to understand, if you had 7, then there'd be a closest one to the origin, and the distance, wouldn't the distance...
Well, no, okay, sorry. If there were 7, they have to branch at the origin. Yes, if there's 7, then right, that's a problem. You're right. There might be 7, but they branch instantly at the origin, and so you might somehow have, you might have a construction based on 4 quadrants where there's always one going northeast or one going northwest, etc. And actually, Who knows? Again, I have my weird Hammersley process. In the finite world, you can do that. It's kind of it's an amazing thing that on a Poisson process, you can put edges such that exactly one goes in each of the 4 quadrants. It's very implausible. You actually can. Probably not here. Anyway, so there's, again, I believe that any sort of nice model in this class does have a unique semi-infinite geodesics. It's sort of one of many technical open questions, because I'm the only person who's ever thought about this so far as to...
All these motions extend to a map in d dimensions?
Probably. I just haven't, I like pictures and data at least somewhere 3 steps away in the background. I don't really have any pictures of this in 3 dimensions. And you have different... In d dimensions, well, let's say 3, okay? But, I'm really thinking of road maps, and it's very hard. I don't know what I want to think about, because, the interesting three-dimensional networks are the neurons in your brain, and those are just different from road networks. So if you actually want to think about 3-dimensional things, you just think about neurons and something concrete and not just make math stuff up. That's my take. Yeah, you want some guidance. If you're going to make math stuff up, you want some guidance as to what you're actually doing. So, so some of right. So I'm sticking to the planar case. The planar case puts in some constraints on things. So the sort of uniqueness of semi-infinite geodesics sounds a sort of a weird pure math property, but because of scale invariance, assuming they are unique, what it's basically saying is that if I take sort of a circle of radius 1 and now take things very far away, then it basically says that there's one path from 0 to the circle of radius 1, such that to every path to a far away point starts off in the same particular way. So that's basically what unique semi-infinite geodesics are saying. And now I can kind of scale everything back in, and this is equivalent to saying, let me sort of wander over here. This is basically equivalent to saying that if I start here and look at paths out to the boundary of the unit circle, then these actually coincide within some small epsilon here. And this is kind of getting us to a sort of path continuity property. So I want to say, here's the route from this point to this point. What happens if I start near here and start near here? I want to say those routes converge. And converge in a strong sense of sort of being identical outside of neighborhoods. And somehow, it's almost the same property as unique semi-infinite geodesics, because any path that goes a fixed distance kind of has to start off the same way. And we are, again, at a technical level, not exactly the same condition, but we're almost in the same ballpark, talking about continuity of paths as a function of the endpoints and more abstract things like semi-infinite geodesics. Okay, so there's a sort of a sales pitch. So here's a sales pitch, which isn't entirely serious, or could be done better, but how your car GPS defines routes. So there are kind of 2 extremes what it might be doing. Remembering that for all of 100 million street addresses, it's going to find the route between. You could sort of imagine your sort of 100 million by 100 million table that was pre-computed, and you just looked up. Or the other extreme, you could imagine it's just representing the graph and doing no pre-computation, and you're just using the classical shortest path distress file algorithm to find it. And so both of those are slightly non-optimum, and after people thought about this for a while, because there are many sort of practical things that go into it, but sort of one of the sort of theoretical practical issues that these guys in 2007 came up with, in the modern style, you have a good idea, it's a science paper and a patent, is this notion of what they call transit nodes, which is basically just intersections of major streets, major roads, and the idea is if you have any 2 points a long way away, hundreds of miles away, then we have this sort of pre-found and pre-recorded, pre-stored 10,000 special points. You have some sort of theoretical guarantee that the optimum route between your 2 points is going to go through one of these special points close to the start, another special point close to the end. So now you kind of do the discrete algorithm finding the shortest route from your house to some number, 10 or so of these special points in the neighborhood, and similarly at the other end, and then you just look up in your table the sort of distance and the route between each of those 10 times 10 equals 100 possible pairs of local transit nodes. And this is something you can all do in 1/10 of a second, as distinct from 5 seconds for the other ways. So people aren't willing to wait 5 seconds anymore. So 1/10 of a second makes a difference. Anyway, so this is just what I've been told by other people. And so at one level, of course, from a practical point of view, the fact that there are 10,000 of these points rather than 1,000 or 100,000 is an empirical fact. But why is this theoretically true? So during sort of TechFest, I heard a talk by Goldberg about this paper I'm quoting here, and so they have this notion. So they're looking at kind of worst case analysis. So they have this notion of a highway dimension that takes a bit of while to pass, except that it's similar to what I'm doing. So somehow if I fix an R and then say, well, for every ball of radius 4r, so wherever I center my ball of radius r, I want to say that there's some number of vertices such that every shortest route, which isn't too short, passes through some vertex in the set. This is kind of close to what I'm talking about without the probabilistic framework. And the point is that a priori there's an h depending on r. They're taking implicitly taking a super r. For this to be a sort of sensible thing to be doing, you want something like scale-invariance to show that, because if h was changing directly with r, you'd only have to do it on the worst scale, not on every scale. So they give some sort of some rather intricate worst-case analysis.
Sorry, how is h a dimension?
It isn't. They just made it up. They just made up the word. It's nothing. It's not a dimension. Someone said that at the TechFest talk. Maybe Yuval said that. There you go. Great minds think alike. Yes. Yeah. It isn't a dimension. They just made it up. That's okay. Yeah. Yes. Okay. So we can do a little back-of-the-envelope calculation within our model. Of course, we have to, in order to sort of map our model, which kind of infinite scales up and down, turtles all the way up and down to the real world, you have to chop off at some low distance, but that kind of doesn't really affect anything. And basically, again, I'm not sure I want to defend this too much. I mean, because one has to sort of rather arbitrarily compare the sort of costs of these two different algorithms, of the sort of minimum cost path algorithm and doing something with pre-computing and looking up k by k matrices, and these aren't sort of rather directly comparable. But the point is, one could sort of do the sort of details of a cost comparison in some other way, and you'd get out a different answer, but of the same general format. So within the model of SIR-SN, sort of a little back-of-envelope calculation here kind of tells you how the algorithmic cost, the sort of time to do an algorithm, scales with various parameters of the model. And the point is it comes out simple and interesting. It depends on the number of edges in the graph, the number of road segments, and our magic number p of 1, and implicit constants there are, of course, the implicit constants in the costs of the algorithms here. So we actually kind of can fit this slightly into algorithmic problems. I'm running out of time, so I'll take 1 minute. That's my last thing. So people paying attention to the logic of what I'm doing will have noticed that I've defined a class of problems, but not shown it's non-empty, a class of models, but sort of not shown it's non-empty. So I've written down a bunch of axioms, and we can prove things from the axioms, but there better be something that actually satisfies the axioms. So again, I'll say in the last 2 slides what something is. Again, it's conceptually simple, though annoyingly hard to nail down details. People who've paid attention to the road network here, 148th Street is the main street, 140th Street is the next main avenue, 140th Avenue, then 132nd Avenue, then 116th Avenue, because there's a park in the way. But so the designers here, road designers, every 8th street and avenue, very roughly, is a major one. So I'm kind of doing the,
I don't think it's the road designers. These are the quarter sections.
These are the what?
The quarter sections.
The
Fields of half a mile by half a mile.
Right, but I don't think this was ever fields in Overlake. I don't think they're ever literally fields. I mean, I think the sort of I think cities were laid out rather separately from Puritan. I don't know, but I think this is all forest and didn't get to be fields, but I could be wrong. Yes, yeah. So the model is I start off with my regular Manhattan grid, but all the sort of odd-numbered streets and avenues have relative speed limit 1, and then the sort of things that are divisible by 2 and not 4 have a faster speed limit. The streets and avenues divisible by 4 but not 8 have a faster speed limit. So you just have this sort of binary hierarchy speed limits, and now you define routes as shortest time routes, which basically means that when you start off with a kind of a starting point and an ending point, and somehow somewhere between these two is the kind of fastest route that way, some ways a fastest route that way, and you're probably going to want to go sort of along here and along here for a while, and then sort of take off somewhere into there. So there's one has routes within this world, but they're sort of preferentially going to the high-speed roads, which are done in this sort of binary hierarchical way. And so that's the basic construction, and the key feature of this construction is that it's actually invariant under scaling by 2. So it's kind of precisely invariant under scaling by 2. The kind of a route from one point to another point, if I scale by 2, then that map takes on to some route from twice C1 to twice C2, and that's actually the optimum route from 2C1 to 2C of 2. So kind of we have a sort of deterministic invariance under scaling by 2 here, and that kind of gets us started. I mean, that's a very sort of strong and special property, so that we kind of keep going by, we now start refining into half, and this consistency property doesn't alter the routes we've already got. We just sort of get in more points, more routes when we refine by half. Intuitively, we can now define routes between points in the continuum by just taking limits in the lattice. From the lattice points, that turns out to be the technically hard way of doing it, showing you get unique limits, but it eventually works. And then, of course, we have no translation invariance. The axes are special, but you just randomly translate a long way away and take weak limits, and kind of general abstract nonsense gives you translation invariance. Again, you just artificially apply a random rotation invariance. And the fact that everything's invariant under scaling by 2 kind of deterministically means you just sort of add a random scaling factor between 1 and 2, and that gives you exact scale invariance. And again, at the end of the day, you've got to do little calculations to show our parameters are finite. So this all takes 12 pages to say the details of, but the other kind of hard part is the kind of what you think is easy. It ought to be easy to just take limits, and it's just hard to show you get unique limits, partly because we don't actually understand algorithmically, or I don't understand algorithmically well enough what the optimum routes are. Anyway, I'm going to stop there. So thank you for your attention. Lots of technical open problems for people who like technical open problems. Thank you. Right.
So you define some conditions, some axioms, some implications, I guess, with this whole net. I'm not quite sure exactly what to remember from this talk.
What to remember?
Like, is there a theorem
right. I mean, it's a
or
very
definition,
special.
or-
It's a special situation. My sort of propaganda is the philosophy here that kind of we have, let's go back to, that there are kind of weird, math modeling started with, Newton and the law of gravity and Kepler and motion. So we've sort of gone, math modeling or probability modeling has gone a long way from sort of basic physics, and we've still kept the style of imagining that complicated things can be modeled simply. And my philosophical point is that we do a bit too much of that. There's John Doyle has this, there's all this argument with kind of complexity theory and that,
You said the road networks should satisfy this and that.
No, I'm going to a math model. I'm doing I'm not claiming this is a very literal model of math, of road network. So this is sort of mathematically playing around, inspired by road networks, but sort of doing things with numbers at the end, which are kind of checkable rather than order of log n theory that kind of doesn't correspond so much to anything that's empirically checkable. So it's sort of a theory, right, it's sort of playing around with theoretical structures for things that are sort of hard and maybe impossible to model sharply.
I have a question.
Okay.
If you take the road network in the US, what's P of 1?
I think about 2.5. Yes, I mean, the more important issue is to what extent is it in fact roughly scale-invariant? We have a theory of being roughly scale-invariant, and what is it? And again, I don't know because it's hard to find out. The best evidence is again from part 2 here, where they did something slightly, so they actually asked. Maps for routes between points a long way apart, and then looked at how much segment was on one named road, how much of the journey was on I-5, I-90, etc. And there's some proportion of the journey on the sort of largest road with the same number, etc. And so if it was scale invariant, all these proportions would be the same on different scales, and the first one varies a little, the other ones are sort of remarkably close to each other. So that's sort of one bit of evidence for scale invariance. Something I have as an undergraduate project when I find an undergraduate to do it is just actually do my little sort of transparency project, look at 4 points in a square, put them down at random, look at the actual subnetwork of the 4 points. There's some bizarre number of topological shapes of the subnetwork, could be like 45, but probably a few of them come up more often than others. And of course, scale invariance predicts that the frequencies of the different topologies shouldn't vary with scale. And again, one can do something similar and see if they do. And my guess is that they don't vary too much because, again, it's intuitively kind of these things vary in one direction. Things have to be getting some more extreme in one way. But it's very hard to see kind of in which way, what is the actual difference between looking at things a few miles apart and a few hundred miles apart. Routes kind of aren't getting more or less straight. You're not getting, so it's hard to imagine sort of ways in which it changes drastically. I mean,
this number that you gave, that the US has 100 million addresses, but there are 10,000 points that would suffice. Does that apply to the other countries developing?
Yeah, I mean the only one they did sort of Europe. So the people who are doing this stuff, they've kind of thought about the US road network and the sort of European road network, and they get sort of very similar. Well, no. I mean, obviously, it's not a. I mean, the numbers aren't the same. It's like the entropy of different languages isn't the same, but we're not assuming it is. Again, it's this whole business of it's not a model, but it's a class of models. Right. So we really want. So that's getting back to my conceptual point that one doesn't want to try and model complicated things like language or road networks as something with 3 parameters or 17 parameters. One wants to think of them as sort of something in a sort of large class of processes defined by structural properties, and yeah, and play around with that idea. Yeah.